Hello class, it's me again. I just found one question that I think that it will be interesting for you to work on, which is the combinations of the chapter 9 on steady-state power analysis and chapter 11, which emphasize on polyphase circuit. And as you can see from this picture, that there's a combination of these two chapters. One is this is information about chapter 9, knowing how to convert information from apparent powers with the power factor lagging and then put it into a complex form or vice versa. And this is a block that connect with the three phase, as you can tell, and then this two part is basically the polyphase that we've been through it before. So the very important step that you have to go through first is to determine what kind of information is given. And you know that for the per phase analysis is convert everything into a Y connected configuration, and in this case is actually already in three phase form. This is beyond the level of the class. If this the voltage between the three phase are totally different with different magnitude and different angles, which is not 120 apart, and if this resistor is completely different values. But this is not the case. This is apparently a balanced system, as you can tell, because I have this R as the same value, which is the R value here, which is the R value here, which is 3 ohm, and then VABC is actually 500 volt with a 120 degree apart. And as you can tell here, this is apparently is a positive sequence, which is a ABC sequence, right? Because you can see that there's a minus 20 degree and a plus 120 degree, which minus 240 degree is the same as plus 120 degree. So very first step you have to do is normalize all this informations, and to do that is not really too difficult. The only inconsistent on this schematic is the delta connection here. So if you remember that, how do you want to convert that delta connection information for all same value, which will be divided by 3? So I thought that the first question is just right on time, because it was asking for find the equivalent Y connected impedance RY for the three phase delta connected load R. So in this case, the RY will be the R delta, which is given here, divided by 3, right? And that will be 3 divided by 3, that give you 1 ohm. And if you will have to draw that diagram, that will be basically the three connected Y value, and each of this is 1 ohm. It's pretty straightforward, isn't it? So this will give you the better information, because if you have this in the Y, this in Y, and then presuming that this is also in Y, everything will be very easy to make it into per phase analysis. So so the part B is asking for find the current phase I2, which is this I2. And then so to find out I2, you have to know the voltage between these two terminal. But first, I think it's best for us to draw a one phase diagram. So you have a voltage source, and in this case there is no sending resistor here, so simply jump into the resistor here, which consists of 1 ohm. That's the part that we are talking about. And let's say we pick phase A, and in this case you have what, 500 volt, and this is actually line to neutral, because this, if I give it to you in A B, that will be completely different. So this information will be just simply 500 volt. And to find out the current going into this, since we don't have any resistor in between that, you can use this voltage, because the voltage here will be equal to the voltage at these two terminal. And to find out the I2, it will be simply I2 equal to VA divided by RY. Right, RY we just found it 1 ohm. VA is 500 volt, so that give you 500 divided by 1, that give you 500 ampere. So if I will have to write it more precisely, I can just say 500 with a 0 degree in this case, right? So that's the solution for IA, and that's what they are asking for exactly. So the next step would be find current phase A and IA and I1. So that would be I1 here, and then IA. So to give you the relationship between I2, I1, and IA is actually based on KCL, right? The sum of current at that node will be equal to 0, and that means if I will have to write it mathematically, IA will be equal to I2 plus I1, right? We just found I2, so the only thing that we had to find is first find I1 and then find IA. How do we find out I1, which is going into this box? And as I said before, you have to consistently using the same information here. So 3 kilo kVA with a power factor of 0.707 lagging. This is actually a three-phase box because you can see 1, 2, 3, and this is a total power is given. So which means that you will have to use this information divided by 3 because you are treating it as a per phase analysis. And to begin with that, you have to find out the angle information, which is given in the power factor. So how do you find out the angle information? So you recall that cosine theta will be the power factors, and then if you know that what the power factor would be, in this case is 0.707, then you have an angle information of cosine 0.707 that will give you 45 degree. So once we know that when this is a 45 degree, the next step will be to find out this S per phase, which is 1 kilo divided by 3. But we are not quite done yet. That 3 kilo is actually the apparent power, just the magnitude. So you have to include the real and the imagined part of it. So this is, in this case, is cosine 45 degree, and then J sine 45 degree. So notice that I haven't put the sign here. So in this case, if you have lagging, it's gonna be giving you the positive sign right away. This is the thing that I talked about earlier the semester, so don't forget that and stick with it consistently. And this will give me the value of equal to 1 with the 45 degree kVA. So don't forget about this K. This is 1,000 times different. If you don't do it right, you probably will get all this solution doesn't make sense. So but I would need some room here, so I'm going to scale this smaller a little bit so that I can have more room to write. So how do we find out the I1? We're still working on the I1. So the I1 will be the S over V conjugate. Right? Remember, this is a handy equation that we use, actually coming from S equal to VI conjugate. Right? So you have that S which is in the per phase, just perfect. You have 1 with the 45 degree. In this case, we have the conjugate here, so the positive become negative. Right? That's why I'm putting different colors just to show you something you should alert. And then what's next? And then divide by the voltage. And in this case, it will be just 500 because there is no resistor between this different parallel circuits. So all the voltage will be the same as the sending source. So that will be giving you a 500, right? And I think this is not just 1; it's a 1K. Sometimes if you miss that, the solution it will be totally wrong. So that will give me what 2. With a degree of minus 45 amperes in this case, right? And to find out the I'm going to partition this so that I have more room for writing. IA will be just I have written before, IA equal to I2 plus I1. We just found I2, and then I1 and I2. So IA will be 500 0 degree plus 2 minus 45 degree, and that gives you 501.42 with 0.16 degree amperes. So that's the final solution for that. So I'm going to circle all what we have found: IA, I1, and I2. So pretty straightforward, isn't it? All this question is only if you understand the setup and how you're going to systematically convert the information into per phase, then dealing with all this information will be much easier. But if you got confused, you probably will get things wrong somewhere around along the step. So I strongly recommend you to actually look through this carefully and understand it. If you don't come to the tutorial section on Sunday, or make an appointment with me on during office hours, or during the week, and I will be more than happy to discuss with you further. Thanks.